Hello, everyone. Welcome to this webinar. So let's just wait a few minutes to see if anyone else is joining, and we'll start in 5 minutes, maybe. Okay, so I think we can start. Hello, everyone. I hope you can all hear me well. My name is Tânia Esteves. I'm a researcher at INESC and a PhD student at University of Minho. And I'm here today to introduce you again to this initiative, which is a joint webinar series between BigHPC project and the UT Austin Portugal Program. I wish to thank you for participating in this session. In this webinar, we welcome Rohan and Kadekodi from UT Austin, who will talk about building high-performance storage systems for persistent memory. Rohan is a PhD student working with Vijay Chidambaram. He works on building system software for persistent memory. In particular, he has built file systems for persistent memory that are aimed at accelerating legacy applications, as well as newer applications that are developed for persistent memory. As I said before, my name is Tânia Esteves, and I will be the moderator of this session. I'd like to inform you that you can and should interact during this presentation. To do so, you can use the chat to share your questions, but during the presentation, there are no discussion moments. There will be, at the end of the webinar, we will provide some minutes to discuss all the questions and interact directly with you. In the meanwhile, I will be monitoring the chat activity to ensure that all the questions are dealt with by the speaker at the right time. Now we can move to the presentation. So Rohan, the screen is yours. Please feel free to start.
Hi, thank you for the introduction. I'll just quickly share my screen. Are you able to view my screen, my slides?
Yes.
Okay, so thank you for attending this talk. My name is Rohan Kadekodi, and today I'll be speaking about building high-performance storage systems for persistent memory. So Optane DC persistent memory is a new memory technology by Intel. It is a non-volatile and fast medium, meaning that it can retain data across power cycles and has low access latencies. We show the access latencies of different memory and storage technologies in the bar below. As we go from the left to the right, the access latencies become higher. On the left end of the spectrum, we have the L1 cache with access latency of around 0.5 nanoseconds and DRAM with an access latency of around 100 nanoseconds. Both DRAM and CPU caches are volatile memory technologies. On the right end of the spectrum, we have the secondary storage devices. So hard disks have an access latency of in the order of tens of milliseconds, while SSDs have access latencies of around hundreds of microseconds. Persistent memory has an access latency of around 300 nanoseconds and is non-volatile. So persistent memory kind of blurs the gap between slow secondary storage devices and fast volatile memory. In particular, loads on persistent memory have a latency of around 300 nanoseconds and bandwidth 1/3 that of DRAM, and stores have a latency similar to DRAM, which is 100 nanoseconds, but the bandwidth is 1/6 that of DRAM. Due to its non-volatile and low latency access, persistent memory is deployed alongside DRAM on the memory bus instead of the I/O bus used for other storage devices. Both DRAM and persistent memory are managed by an integrated memory controller. There are two modes in which persistent memory operates. The first one is called memory mode. In this mode, persistent memory is exposed as DRAM by the hardware, and DRAM is used as a direct mapped cache for persistent memory. In this mode, persistent memory acts as a volatile medium and cannot retain data across power cycles. The second mode is called the app direct mode. In this mode, persistent memory acts like a storage device and is exposed separately as a block or character device. In this mode, persistent memory can retain data across power cycles, and DRAM is not used as a cache for persistent memory by the hardware. With the introduction of persistent memory, there have been changes in the Linux kernel to support persistent memory. In direct access, persistent memory can directly access applications can directly access files on PM using loads and stores directly from user space without going into the operating system. So there is no copy of data kept in the page cache in DRAM with DACs. In comparison, for other storage media like hard disks or SSDs, the DRAM's page cache lies in between the applications and storage and acts as a cache for the underlying slow storage. So due to the low latencies and high performance of PM, there are a number of applications that can take advantage of persistent memory. First, we have legacy applications. These are applications that are actually written for other storage media, but can benefit from the low latencies of persistent memory. Examples of these applications are databases like MySQL, MongoDB, key value stores like RocksDB, and utilities like rsync and so on. Then we have new applications that are built for persistent memory, and these also include databases like Memhive, caching services like Twitter's Pelican Cache, and Memcached, which now supports persistent memory, and frameworks like PMDK or Persistent Memory Development Kit by Intel, and so on. The goal of this talk is exploring ways to achieve high performance for various applications on persistent memory. To achieve this goal, we first identify two classes of applications that use persistent memory in different ways. The first class of applications is called POSIX system call applications, and the second class of applications is called memory mapped applications. We then build systems to enable both the classes of applications get the best out of persistent memory. So we start with the first class of applications, the POSIX system call applications. The typical way in which legacy applications access their data on persistent memory is by talking to a file system. The way applications talk to a file system is through the POSIX API. POSIX contains API to create, open, read, write, rename files, and so on. There are different persistent memory file systems that implement the POSIX API. The examples of such file systems are ext4 DACs, PMFS, Nova, Stata, etc. An important production file system that is used with persistent memory is ext4 DACs. It is the modification of the ext4 file system for persistent memory. ext4 DACs is under active development by the ext4 community, which consists of thousands of contributors. ext4 DACs works with modern Linux kernels and is the only persistent memory file system that is widely used. In spite of this, all file systems, including ext4 DACs, suffer from something called software overhead. Consider a simple operation of appending 4 kilobytes of data to a file. In this graph, the x-axis shows different file systems used, and y-axis shows the time taken. So lower is better. The time taken to simply copy 4 kilobytes of user data to persistent memory is about 700 nanoseconds. ext4 DACs takes about 9,000 nanoseconds compared to the device latency simply to append 4 kilobytes of data to a file. So software overhead is the ratio of the time taken for a file system to service an operation versus the time taken for the device. So ext4 DACs has a software overhead of 12x over and above the device latency. Other state-of-the-art file systems on persistent memory suffer from software overheads ranging from 2.5x to 5x. So this experiment shows that existing file systems suffer from high software overheads for common operations such as file appends, and ext4 DAX, although widely used, suffers from the highest software overhead among other state-of-the-art file systems. To solve this problem, we present SplitFS, which is a file system that is designed to minimize the software overhead in file systems. SplitFS lies in user space and kernel and serves data operations from user space and metadata operations from the kernel using the maturity of ext4 DAX. SplitFS provides strong guarantees to applications such as atomic and synchronous data and metadata operations similar to other research file systems like NOVA. SplitFS reduces the software overhead by up to 15x compared to ext4 DAX and improves application throughput by up to 2x compared to NOVA. SplitFS is open sourced on GitHub. SplitFS adds a new data point in the design of persistent memory file systems. If you consider a spectrum of design points in building file systems, then on the left end of the spectrum, we have file systems such as ext4 DAX, PMFS, and NOVA that are completely in the kernel. The disadvantage of these file systems is that they suffer from low performance or high software overhead because of frequent kernel crossings and complex code paths for all file system operations. On the other end of the spectrum, we have Strata, which is completely in user space. While Strata manages to reduce the software overhead, it suffers from high complexity because of having to essentially re-implement the entire VFS layer in user space. Then we have ARI, which is mostly in user space and relies on the kernel for certain coarse-grained allocations. ARI also suffers from high complexity and actually optimizes for an API that is different from POSIX. SplitFS adds a new design point in the spectrum, which is a file system that is partly in user space and partly in the kernel. SplitFS achieves high performance by servicing data operations from user space and reduces complexity by routing metadata operations to the mature ext4 DAX. The highest performance of SplitFS comes from accelerating data operations from user space. This is because data operations are very common and are simple to implement and offer the maximum performance boost when handled from user space without kernel overheads. The low complexity of SplitFS comes from using ext4 DAX for the metadata operations. Metadata operations are rare and complex, and POSIX has a number of complex corner cases for these operations. SplitFS uses ext4 DAX's maturity for these complex rare operations. We now discuss the overview of SplitFS. As discussed before, SplitFS lies both in user space and kernel. The user space component of SplitFS is called uSplit, which binds to individual applications. The kernel component is ksplit, which is ext4 DAX that is shared between applications. All the read and write calls made by the application are intercepted by uSplit and are serviced from user space. All the metadata operations such as creates and deletes are routed from uSplit onto ksplit, which is basically ext4 DAX. SplitFS also maintains an operation log per application for achieving stronger guarantees such as synchronous operations. So SplitFS accelerates common case data operations while leveraging the maturity of ext4 DAX for metadata operations. SplitFS uses operation logging and out-of-place updates for providing atomic and synchronous operations. Let us now see how SplitFS handles data operations like file reads and updates. Consider that we have an application in user space, SplitFS both in user space and kernel on persistent memory. When an application tries to first read or update a file, uSplit intercepts the call, memory maps the portion of the file that needs to be read or updated underneath the hood. SplitFS maintains this memory mapping in user space using DACs, as explained before. All reads and updates to that portion of the file are then served using loads and stores from uSplit without going into the kernel. When there is a read or update to some other region of the file, then that subsequent portion of the file is mapped. And all reads and updates to the mapped regions are served from user space. So SplitFS maintains a list of memory maps per file to satisfy reads and updates. In the common case, all reads and updates to a file are serviced from user space and do not pass into the kernel. However, this raises an interesting question. What happens when an application just keeps appending to a file? Does that lead to high overhead due to constantly mapping new regions of a file on the write? To see how that is handled, we see how SplitFS handles file appends. Note that this is the same operation that we saw before in the motivation numbers where other file systems suffer from high software overhead. Consider that we have a file foo on persistent memory. When an application starts, SplitFS creates a special file called staging file on persistent memory. The staging file is mapped into user space by uSplit using DACs. When an application tries to append some data to file foo, uSplit intercepts the append operation and redirects it to the staging file from user space. A read request to the appended data is also intercepted by uSplit and serviced from user space from the staging file. When an application later calls fsync, SplitFS goes into the kernel and issues a new system call named relink. Relink creates an ext4 journal transaction containing the inodes of file foo and staging file. Then the extent containing the appended data is moved from the staging file to file foo. Note that relink is a purely metadata operation and does not involve any data transfers. In this way, file appends are handled completely from user space using staging files by uSplit and do not pass into the kernel. This technique of handling file appends is called staging and relink in SplitFS. SplitFS uses a few other techniques for reducing software overhead, which I cannot go into the detail due to lack of time. However, I provide a summary of the techniques along with their benefits here. First, the split architecture is used by SplitFS for low overhead data operations and correct metadata operations. The staging and relink technique is used for optimized appends. SplitFS uses a collection of mmaps technique for low overhead data accesses. And SplitFS employs optimized logging and out-of-place writes for providing stronger guarantees of synchronous and atomic data operations. We now move on to the evaluation of SplitFS on Intel Optane DC persistent memory. We compare SplitFS with other state-of-the-art file systems, but focus on Nova in this evaluation. We answer the following questions in evaluation. First, does SplitFS reduce software overhead compared to other file systems? And second, how does SplitFS perform on real legacy applications? To answer the first question, we discuss the same experiment as before, and we look at the software overhead of SplitFS for file appends. SplitFS suffers from the least software overhead in the most strict mode, which guarantees synchronous operations and data atomicity. The staging and relink optimization helps SplitFS achieve minimum software overhead. Next, we compare the performance of SplitFS with the next best file system, which is Nova, on the YCSB workload suite. YCSB is an industry standard macro benchmark used to evaluate databases. We run YCSB on the LevelDB key value store by Google, which stores its data on SplitFS and Nova. The y-axis shows normalized throughput with respect to Nova, while the x-axis shows the different standard workloads of YCSB with different read-write ratios. SplitFS outperforms Nova on all of the YCSB workloads. SplitFS is better by up to 2x on the write-heavy workloads. Write-heavy workloads get maximum benefit from SplitFS due to the optimized appends and the split architecture techniques that I summarized before. So SplitFS introduces a new architecture for building persistent memory file systems that reduces software overhead, provides strong guarantees, and leverages the widely used and mature ext4 DACs. SplitFS is open sourced on GitHub and is published in SOSP 2019. Okay, so now we move on to the next class of applications, which is the POSIX memory mapped applications. Memory mapped applications access data on persistent memory from user space without going through a file system. So there is no way in which a file system like SplitFS can interpose on reads and writes for these applications. These applications first allocate files on persistent memory using a persistent memory aware file system. They then perform DAX mmap to map the file into user space themselves. And due to DAX, there is no data copy from persistent memory to DRAM on memory mapping. So physical addresses on persistent memory are directly mapped to virtual addresses in the application's address space. After mapping, the applications perform direct loads and stores to the allocated space on persistent memory from user space without going into the kernel. The first access of a page leads to a page fault that sets up page table entries for converting virtual addresses to physical addresses on persistent memory. Frequently accessed pages are cached in the TLB or translation look-aside buffer for reducing address translation overhead. Page faults and TLB misses take up to 60% time of the mem copy or copying of data when we are copying an entire page. The performance of memory mapped applications depends on the number of page faults and TLB misses incurred by the applications during runtime. To alleviate the overheads of page faults, modern hardware and kernels support huge pages, which are basically larger pages of 2 MB or 1 GB in size. Huge pages reduce the number of page faults and TLB misses by up to 500x. File systems need to allocate files using aligned and contiguous 2 MB extents in order to be mapped using huge pages. Consider the file on the left. It is fragmented and not contiguous to 2 MB extents and cannot be mapped using huge pages. The file in the middle is contiguous in 2 MB, but is not aligned to 2 MB extents and again cannot be mapped using huge pages. Finally, the file on the right is aligned and contiguous to 2 MB extent and 2 MB boundaries and can be mapped using huge pages. So file systems are responsible in issuing huge pages to memory mapped applications as they are involved in the placement of files on persistent memory. File systems must preserve huge pages with age. And this brings me to the next topic of what is aging and why should we care? Aging is the state of file systems as a result of constant allocations and deallocations over a long period of time, typically years. Google, in their talk about cluster storage systems, mentioned that they want to keep disks full and busy in order to avoid excess inventory costs. The figure on the left shows their disk utilization, where every box is a disk and the colors show the disk spindle utilization. As we can see, majority of the disks are almost completely utilized and the free space is very fragmented. Thus, aging leads to fragmentation of free space, increasing the number of page faults in memory mapped applications. For measuring the impact of aging on file systems, we perform a simple experiment where we memory map a 1 GB file and perform sequential writes using mem copies of 4 KB each to the file. We age the file systems using an open source aging tool that does numerous allocations and deallocations to fit a size distribution, directory depth distribution, and age distribution. We end the aging at different utilizations of the partitions as shown in the x-axis. The y-axis shows the bandwidth of memory memcopy commands where higher is better. When freshly created, ext4dax is able to achieve a bandwidth of higher than 4 GB per second. However, when aged, the bandwidth of memcopies on ext4 drops as the utilization increases, and at 60 and 90% utilization, the bandwidth of aged ext4 DAX drops by more than half compared to freshly formatted ext4 DAX. Similarly, the bandwidth of Nova also drops when aged, especially at higher levels of utilization. So aging significantly degrades the performance of other file systems like ext4 DAX and Nova. To solve this problem, we present WineFS, which is a huge page-aware file system for persistent memory that ages gracefully. WineFS uses a novel alignment-aware allocation policy to preserve huge pages. WineFS achieves high performance for a wide range of applications that access files using memory mappings as well as POSIX system calls. WineFS is designed to achieve high scalability and works well with multiple NUMA nodes. The performance of WineFS stays the same when aged. Moreover, in some memory mapped applications, aged WineFS actually performs better than freshly formatted Nova. WineFS is open sourced on GitHub. We now discuss the insights behind WineFS and the techniques used by WineFS for achieving high performance. The first insight is that file systems need to allocate files on aligned and contiguous extents in order to be mapped using huge pages. Existing file systems like ext4dax and xfsdax strive to preserve the contiguity of free space with age, but fail to preserve the alignment of free space. WineFS uses an alignment-aware allocation policy that focuses on contiguity as well as alignment of free space for allocating huge pages to memory mapped applications. Let us discuss the alignment-aware policy of WineFS. Consider that the free space contains fragments that are as follows. Fragments on the left are small and non-aligned, while the fragments on the right are aligned to huge page boundaries. WineFS maintains two data structures in DRAM for managing this free space. The holes or unaligned extents are managed by a red-black tree, and the huge page aligned extents are managed by a linked list. A small allocation request of lesser than 2 MB is forwarded to the red-black tree and satisfied by a hole. 2 MB allocations are forwarded to the huge page list and use up an aligned 2 MB extent. Allocations that are larger than 2 MB are broken down into multiple smaller allocations of less than equal to 2 MB each. All the 2 MB allocations are then satisfied by the huge page list, while the smaller allocations are satisfied by the red-black tree containing holes. A small deallocation request is forwarded to the red-black tree, and if there is a contiguous free extent to the deallocated extent, it is merged. If the merging results in a 2 MB aligned extent, it is moved to the huge page list and huge pages are reclaimed. So to summarize, WineFS places large files of memory mapped applications in aligned huge page extents and small files of the POSIX system call applications in unaligned holes. WineFS aggressively reclaims huge pages on file deletions and deallocations. The second insight of WineFS is that file systems should achieve high scalability for POSIX system call applications without causing fragmentation of free space for the memory mapped applications. The per inode log of Nova fragments free space, and the per process log of Strata wastes Hugepages by using them up for the system call applications that essentially do not need Hugepages at all. WineFS chooses a suitable on-persistent memory layout, employs per CPU journaling, and uses a hybrid data consistency mechanism for simultaneously achieving high scalability and huge page preservation with age. We discuss these three mechanisms next. First, let us discuss the on-persistent memory layout of WineFS. WineFS divides the entire persistent memory partition into per CPU allocation groups. WineFS maintains metadata indexes and free lists for every CPU in DRAM. WineFS uses the alignment-aware allocator for every CPU's allocation group in DRAM. WineFS maintains a journal and inode table per CPU on persistent memory. The journal and inode tables help during recovery to rebuild the indexes on a crash. The rest of the free space is used for application data. The key takeaways behind the high-level design are that the per CPU allocation groups and journals and other metadata indexes allow for high scalability in WineFS. Furthermore, the metadata structures such as journals and inode tables are contained in specific regions on persistent memory, and this avoids free space fragmentation. We discussed the second contribution, which is the per CPU journaling used in WineFS for scalable and low-cost crash consistency. WineFS uses a separate journal for every CPU. Each system call in WineFS creates a journal transaction in one of the per CPU journals. Consider the common case in which multiple threads or processes are modifying separate directories or files. In this case, each thread starts a new transaction in its specific journal. There is no synchronization required between these journals. So independent transactions use separate journals in parallel. A global atomic counter called transaction ID is incremented for each transaction, which can be used during recovery. However, consider a case when there are concurrent updates to a shared file or directory. In this case, thread 0 and thread 1 simultaneously create a file in the same directory. A crash during these simultaneous operations can lead to corrupt metadata in a file system unless handled. Thankfully, in such cases, the VFS, which lies above the file system layer in the kernel, grabs a lock on the shared directory, and both the operations occur one after another. WineFS relies on VFS locks for updates to shared directories or files. So only one uncommitted transaction per file or directory needs to be recovered on a crash. So to summarize, WineFS uses per CPU fine-grained undo journaling for high scalability and low-cost crash consistency that avoids free space fragmentation. In the common case, when every thread updates its own file or directory, there are no locks required, and each thread can use its own specific journal. The correctness of per CPU journaling is guaranteed through VFS locks for shared files or directories and managing thread migrations. We now move on to the last contribution, which is hybrid data consistency mechanism in WineFS. Consider the free space of an allocation group as shown below, containing some holes and some aligned extents. File 1 is a small file belonging to a POSIX system call application and hence is allocated in an unaligned extent. File 2 belongs to a memory mapped application and is allocated in a huge page aligned extent. As shown before, the free space of the aligned extents is tracked by a red-black tree. On receiving a file update for file 1, WineFS uses copy on write to avoid excess data copies and uses up an unaligned hole for the new updated data. So files of POSIX system call applications are updated using copy on write to holes. This avoids fragmentation of free space due to files that belong to system call applications. A file update for file 2 does not use copy on write, as that will fragment the file and will not allow it to be mapped using Hugepages. Instead, a file update for file 2 updates the data in place with the help of data journaling. So files of memory mapped applications are updated in place using data journaling. This avoids fragmentation of memory mapped files and allows them to be mapped using Hugepages. Let us now summarize the techniques of WineFS along with their benefits. The alignment-aware allocation policy helps in managing contiguity and alignment of free space. The on-PM layout helps in achieving high scalability while avoiding free space fragmentation. The per CPU journaling achieves high scalability while avoiding file fragmentation. WineFS uses a hybrid data consistency mechanism that provides strong consistency guarantees while preserving huge page aligned extents with age. We evaluate WineFS on persistent memory and compare it with state-of-the-art persistent memory file systems that lie in kernel and user space. We answered two main questions. How does WineFS age, and how does WineFS perform on memory mapped applications? We first check the performance of WineFS on the same experiment as before. The performance of WineFS consistently stays at higher than 4 GB per second with increasing utilization when aged. We now measure the performance of WineFS on the same YCSB workload suite that we used for SplitFS. We run YCSB on top of the RocksDB key value store with memory mapped reads and writes. The y-axis shows throughput with respect to ext4 DACs, so higher is better, and on the x-axis we have the standard YCSB workloads. WineFS outperforms all other file systems on all of the YCSB workloads by up to 1.5x. Note that WineFS performs better than SplitFS since this is a memory mapped application and SplitFS does not optimize memory mapped applications. WineFS suffers from 30x fewer page faults compared to Nova in YCSB load workload. So WineFS demonstrates that it is possible to design a file system that achieves high performance for memory mapped applications, achieves high performance for POSIX system call applications, and maintains the high performance in the presence of aging and under high utilization. We have open sourced WineFS on GitHub and it is published in SOSP 2021. So SplitFS and WineFS help us achieve our goal of achieving high performance for a wide range of applications on persistent memory. So to conclude this talk, persistent memory is a non-volatile and fast memory technology. Applications access persistent memory in different ways. The first way is by issuing POSIX system calls such as reads and writes, and the second way is by memory mapping files using loads and stores. This talk tries to answer the question, how to achieve high performance for both these classes of applications. And to answer the question, we present SplitFS, which accelerates system call applications using a novel user kernel split. And we present WineFS that accelerates memory mapped applications via huge page preservation. With this, I end the talk and I'm happy to take questions. Thank you.
Thank you, Rohan. It was a really great talk. We now have some time for questions. So as I said in the beginning, you can either write your questions on the chat or you can ask us and we will give you the necessary permissions so you can ask questions directly to the speaker. So we have here Ricardo Macedo. So can you unmute?
Can you hear me?
Yes. Okay.
Yeah.
Okay, so thank you, Rohan, for the very nice presentation. I have actually two questions. One of it is, so for my understanding, I don't know if you are aware of PMDK, but now you can basically combine PMDK with ext4 DEX. And I think you have the same guarantees as SplitFS in POSIX modes, right?
So PMDK is like a memory mapped application, right? That does loads and stores from user space. So SplitFS does not really optimize these memory mapped applications. SplitFS is used for system call applications. So yes, if you use PMDK on SplitFS, it will just redirect everything to ext4
Yeah.
DAX. Yeah.
Exactly. And in that case, we probably would be best served using WineFS, right?
Yes, that
Yeah.
I believe. Yeah.
Okay. And I have another question is that, have you tested this either SplitFS or OneFS with multiple applications sharing the same device?
So we have tried WineFS, but not SplitFS with multiple parallelly running applications. We mostly target like low latency data center level applications where normally you have dedicated, where they run on their dedicated nodes such as RocksDB and stuff. But I don't like in terms of correctness, I don't see a problem. But we have not measured them in terms of performance, if that is your concern.
Yeah, yeah. For my understanding on, I have read both papers, but I think from the crash consistency side, you would not have issues, right? But from the performance one, it would be really interesting to see different applications with different access patterns sharing the same device, right? But because it will generate similar patterns as the POSIX file system ones, where we have multiple applications sharing the same device, deals with the contention, and it would be really interesting to see these PM-aware file systems. How do they behave under these scenarios, right?
Yeah, I agree. That is an interesting thing. Yes. And I'm actually like in the right, like on the way of writing my thesis and stuff, where one of that is like a goals for me to evaluate. And if that turns out to be bad, then that can be interesting future work also. So yeah.
Okay, great. Thank you.
Thank you.
So I don't know if anyone else wants to ask anything. In the meanwhile, I think I will ask one question. So the policies of WineFS, are they specific to persistent memory, or can they be applied to other file systems that are built on HDDs or SSDs?
Yeah, thank you for the question. So I believe that the policies of WineFS are actually meant for persistent memory because they are meant for memory mapped files using DAX, and DAX is something that is specific to persistent memory. So when you memory map using DAX, persistent memory is directly exposed to the applications without copying to DRAM. So file systems directly play a role in that aspect. But in the case of hard disks or SSDs, when you try to memory map, a copy of the file is created in DRAM. And after that, the file systems don't really have any role to play when accessing that data. So our allocation policies and stuff work when you use persistent memory and not when you are using a file system on SSD or hard disks.
Okay, thank you. So as you mentioned, SplitFS is not optimized for metadata intensive workloads, right? So if you have like applications that are POSIX system calls based or memory maps based applications, would it be like possible to combine both the file systems, SplitFS and WineFS? What do you think would be the implications of such combination?
So yeah, it is right that SplitFS just like goes to ext4 for the metadata operations. So it actually incurs small overheads for that, while WineFS is actually optimized for metadata operations also. So you can run SplitFS on top of WineFS instead of ext4 DAX. to also get benefits from the metadata operations by implementing the relink system call that I explained in WineFS instead of ext4. But like this is not all is what I believe. I think that you will need to do more, because in file appends, when SplitFS writes to a staging file and performs relink, it moves certain blocks from one file to another. And that actually leads to fragmentation of files. So if you are using WineFS, that will lead to free space being fragmented. So if they kind of contradict with each other, and if you want to use them on top of each other, maybe you will have to move in 2 MB blocks instead of 4 KB blocks. And if you do that, then that could be helpful, but I haven't evaluated how much overhead that will be, because you're copying like a lot of data, or you're copying very big extents at that point.
Okay, thank you. So do you have any question from the audience? Okay, we have here Samuel. Can you unmute?
Yes, I hope you can hear me.
Yeah.
Yes, go ahead.
Just a curiosity from my side. With SplitFS, since you are splitting here the implementation for user space, this seems very, very interesting. For example, for containers, how does this can be merged in that kind of environments? For example, to enlarge the processing environments and load the images and all of that kind of things.
So I'm not really an expert in virtualization or containers. Could you like talk a bit more so that I can then?
Yes. So the idea is I could understand. I don't know if I catch all the idea here, but as I could understand, SplitFS tries to split here some operations that works on user space, right, from
Yes.
the implementation in kernel side. So the idea is if this can contribute to accelerate the I/O operations, even on user space side. For example, when we are creating a container and then just use that file system.
Yeah, that I think that it seems like when I hear it, I haven't thought about it, but it seems like an interesting thing to try out, where if you can spawn a container and then what you're suggesting is that the IO data operations can directly go from user space, while the metadata operations can then be handled by the kernel using something like SplitFS, right?
Yes. So if you have, for example, some tests around that, and if that can be exploited as a kind of good feature for using SplitFS.
Yeah, I think that could be a very interesting thing actually, if the container performances increases a lot with that, because they have higher overhead than just running it on bare metal hardware. So maybe the advantages can be like even more exacerbated if we use it in that context. But that is an interesting point which we should try out actually.
Okay, thank you.
Thanks.
Thank you, Samuel. So last call for questions. So if there is no more questions, I think we can end this webinar here. So okay, so thank you again for your participation and all of your questions. Please stay tuned for the next webinar, which will take place in September. All the details will be shared soon on BigHPC webpage, and the upcoming event will focus on the latest results of the project. So thank you again for joining us, and that's it for today.
Thank you. Hey.
Thank you.
Thank you. Bye, everyone.
Thanks.